students on several course presentations. Jeff has an interesting background in that he has worked in a number of kind of commercially oriented companies, and as well as being at Sun Microsystems, working on kind of more R&D-ish type things. Currently CTO at Blue Fang Games here in Massachusetts, and today he's going to talk to you about some interesting work that he's doing with Zoo Kingdom.
Thanks. So good morning, everyone. I hope everyone's reasonably awake. I hope I'm reasonably awake. As mentioned, right now, what I'm doing right now is that I'm the Chief Technology Officer at Blue Fang Games. Blue Fang is a 10-year-old Boston area game company, probably best known for package games, games like the Zoo Tycoon series. We took a very strong shift, and Blue Fang decided that the future of the company lay in online. That's actually when I came into the company. I have a long background in online game development. I was the senior game integration engineer way back, probably about, what is it now? It's probably more than 10 years ago, one decade ago now. I had a company called Total Entertainment Network, or 10. I don't know if any of you are old enough to remember 10, but 10 was one of the first providers of internet play for packaged games. We worked with the game companies to bring those games online. So we did the online portion of Duke Nukem 3D. We did the online portion of, I worked myself on CivNet, Total Annihilation, an early MMORPG, Dark Sun Online, back when we thought 400 people at the time was massive. And a bunch of other games like that. As was mentioned, I took some time. While I was in 10, I started the project working on an online game technology, which we're actually using, and I'll mention briefly as part of the talk, at Blue Fang now. It was eventually adopted into Sun. I went to Sun Labs. And Sun was called Project Darkstar, now called Red Dwarf, because it has gone, now that Sun no longer exists, in case you know, it was bought by Oracle. Project Darkstar, which was always an open source project, became a completely community project. It's now Red Dwarf. Following that, I went back out to the game industry, which is where I really wanted to be. I was only at Sun because I had a particular technology I wanted to develop. That was a good place to develop it. I spent a year at a company called Rebel Monkey, doing something called Camp Fu. Unfortunately, Rebel Monkey, Camp Fu was actually casual multiplayer games. It was a very interesting company. Unfortunately, we ran out of money last May, or let's see, a year? Yeah, last May. No, August, May before last. Anyway, right in the middle of the worst moment in investing and spending in companies that's probably ever been, certainly in my history in the industry. This was right after the banks crashed, and nobody was investing in new companies. So from there, I ended up being recruited into Blue Fang. I'll talk to you about what we built the Blue Fang. This is actually, I should mention, you're getting a sneak preview. This is a talk I'm giving at the Game Developers Conference in San Francisco, beginning of next year. Yeah, all right. That's right, okay. So talk about, first of all, the big goals. When we're building the system, so what I'm going to talk about is the architecture of our online server system and how it works with the game. We had a couple of big goals in designing this. When you're doing casual games, you have to think really massive scale. Again, I remember when 400 players was massive. We're now talking potentially tens of thousands of simultaneously connected users at a time. This is about more back to bigger even than you have to deal with if you're building MMORPGs. The other half of this is at the same time as more people, each person brings less money. We figure depending on the game, each currently connected user brings us up to somewhere between 10 cents to $10 a month. $10 is the way high end. That's if you've got a very, very successful game. It takes a while to get there with any game. 10 cents is not uncommon. It's 20, 30 cents for games that are not as successful. The other thing about these games is that although there's a lot of misinformation in the sense about them, people talk about how fast and cheap they are to develop. That's true, however, they're actually rather expensive to maintain. We figure there's probably a couple $1 million in Zoo Kingdom at this point, because in order to keep players playing on these free-to-play games and keep them spending money, You have to keep putting out new content. The other half of this that's important is at the same time you have to be massive, you also have to deal with security issues. This is important for a couple reasons. Most of these games are based on microtransaction models. Zoo Kingdom is one example. We make our money by selling basically special animals, selling advantages in the game, etc. All these things only have value because people can't get them without spending money, and because they are reasonably rare and so people want them. If people can cheat to get them, there is no point to spend money. Unfortunately, these goals are at direct odds with each other. We'll talk about it a little bit. We'll talk about how we approach trying to satisfy them both. So this is what this talk is about. We're going to talk about what the server side really looks like and how that affects the game side. The reason for that, and both has to do with security, which we'll get more into, and has to do with the fact that your scaling problems are all on the server. On the client, everybody these days has what we used to think when I was in college, we would call what you have in your laptop a supercomputer, and it's on your desk. So we're not really worried about these very simple games with computer power on your desk. But we are worried about computers that have to handle, as I say, tens of thousands of you at once. There are two ways that are traditional in the social game space. And talking social games, talking Facebook games, and games like this. These really come out of some history I'll talk about a little. The first one is these single-player games where basically you're playing totally by yourself. And you may be able to see your friends' high scores or level, or that's about it. Blue Kingdom actually is basically one of these. It's a little cool that I'll talk about, not a lot. Those traditionally are a client in the front and some kind of database to store the data on the back. When they extended this to multiplayer, what the folks in this industry did was they basically put a socket server in the middle. The socket server is basically just a communication server that allows you to pass packets from one player to another player and back. So, what's a really bad way to build one of these games? Well, a really bad way is to put your database on the internet and connect to it with JDBC or ODBC over the internet from your client. There's a surprising number of games that did this. Why is it bad? It's terribly, terribly insecure. You've exposed your database directly to anybody who has connection to the internet. Yes, you need credentials to connect to it, but those credentials have to be resident on the client's machine, which means they are accessible. We'll talk more about that a little later too, talk more about security. If you use many of the standard sort of enterprise tools, business-oriented tools, this is what you get. And the reason is because those tools weren't built for building internet games. They're built for mostly building intranet applications, things that existed inside of a corporation. And inside of a corporation, you assume the person who's getting access to that application already has some level of right to be there and some level of responsibility. If they hack your database, you fire them. And it's not so easy with internet players. All right, slightly better implementation. And this is what people who know a little bit more about what they're doing tend to do. What they do is they take that and they put a web service server in the middle. A web service server, for those of you who haven't dealt with these, is basically a web server. It's an HTTP server. It runs either servlets or CGI scripts or some form of interactive content on the back end. It takes HTTP requests in as commands and sends back the results as a return for the HTTP GET. So what does this do? Well, first of all, it means that your database, where your real goal is, where all your game state is not directly on the internet. It also means that the web service server holds DB password, not the client, so that isn't exposed outside. It does use HTTP basic communication. This is not a feature. This is a bug, and we will talk about why as we go a little further in. I'm going to throw out a leading question here, and the question is this enough security? And when you think about that, think about the fact that the client is still hackable. Think about what the client has to do in order to connect to this. We'll talk more about that too. So this is the socket server implementation. Very similar. What you do basically is you take usually you take the web server out of the middle, you put what's called a socket server in instead. A socket server is a program such as SmartFox, Electro Server. There's a whole bunch of open source ones. And basically what it is so it's effectively a little custom router, packet router. You all connect to, and it moves packets between players. It also generally provides some kind of abstraction of that database in It may be in forms of storage blocks with keys. It may be in forms of some kind of hierarchical data store with some kind of abstraction. But you can store data in the database. It has to be persistent. You get it back. Now, is this up security? Okay, again, the client is still unprotected. We'll get back to that too. All right, so let's talk about security. I promise I can get here. When you use a client plus database, actually, I'm sorry, let's talk about scalability first. I'm sorry, security is the next slide. Scalability, a lot of these designs are generally pretty scalable. There's relatively low load on the servers because all your game logic is on the client. All the servers are doing is handing me, putting together persistent data. It's possible to horizontally scale them out using existing database solutions. You can either partition out on your database, you can do replication. These are all pretty standard database things. One issue when you're using HTTP is HTTP is quite wasteful. And we'll talk more about it. So we'll talk about later. We'll talk about why this is in detail, but as a little preview, HTTP, every time you put or get a packet, requires creating and tearing down a TCP/IP connection. We'll talk about what that is and then why. It also generally involves text parsing, because HTTP is a text protocol, which is not a huge deal with the power we have these days, but it is still wasteful. If you think about this, you're trying to get bits from one place to another. You have to convert them to text in order to put them out to HTTP, to convert them back from text back to bits on the other end. That's a lot of unnecessary conversion. With the socket server, there's a little bit more load, but it still scales very well. The only load the socket server is dealing with is packet traffic. And if you code that well, that's really pretty efficient. We do modern operating systems. Modern operating systems actually have ways to do things like move data directly from an incoming socket to an outgoing socket without ever bringing it up into what's called user land or the user space. That actually can be very, very efficient. You do have a basic issue, which I'll talk about again more about, which has to do with the n-square problem as you connect more and more users talking to each other. But this is usually handled by dividing up the users into communication groups. You can horizontally scale this out to multiple servers. When you do that, generally what you have to do is you have to take these groups of players who are like playing one game and put them all on one server together. And that's what we say we're talking about interest group or communication group. They, for historical reasons, often are HTTP as well, actually. All right, so security. Well, I chose that picture for a reason. These are not very secure solutions. As I mentioned, the client, first of all, owns the game state. We'll talk about that more too, why that's bad. It also controls the database. It's sending commands to the database. So anybody who can take control of your client can, to some degree, take control of your database. It's a little less exposed if you have a server in the middle that's doing the web service thing. You don't expose the entire database. You only expose specific operations you want to happen. So you can prevent some things that are just outright garbage, such as ruining your referential integrity. But it's still open to the client, and the client is open, unfortunately, to the person who owns the machine the client is running on. When you have a socket server, it doesn't really do anything to that, except because you still need credentials to log in on the socket server, but the credentials are still resident on your machine. Same is true for the web service as well. And now you've got others involved too, so you have all kinds of issues. And now people can affect not just their own game state or the state of stored data, but actually the state of games during play. So the big problem. I hope somebody gets why I used that slide. Client slide. You cannot trust a client. Why can't you trust the client? Well, to begin with, clients can be hacked. And by hacked, I mean people can go into the memory and change what the client's doing while it's running. They can go to the code that's in memory and change the code while it's executing. And in general, they can change the way the client functions. So by changing the way the client functions, they can change what it's telling the server about the reality of the world, and therefore what the server thinks is real. Clients can also be spoofed. And by spoofing, so you can do things, for example, with tools like quick memory editor. You can go in and actually for instance, change how many gold pieces you have in an RPG game by finding the value of memory and changing it. That's hacking. Spoofing, what you do is you actually create an entire fake client. And what you do for spoofing is you actually dig into the client and just find the credentials it uses to say, I exist, I'm real, and you want to talk to me. basically log in password effectively in name. And then you use that in your own program to connect. And now you've got a program that's completely under your control that can do anything you want to, and make any lie it wants to the servers, and there's no way to detect it. The third thing you can do is you can also proxy. The classic example of this was the aimbot in Quake. And what proxying means is rather than talking directly to the server, I put something in between your game client that you gave me and your server you're running. So an example in Quake there's a classic example was the aimbot. What the aimbot did very simply was it was a packet proxy. The Quake game would connect to the proxy would then connect out to the game server. As packets came down saying where people were in the world, the proxy would just make note of that, remember that. When packets went the other direction, saying you were shooting a gun, it would rewrite the coordinates where you were shooting to make sure it hit where the people were. It's an example of a proxy man-in-the-middle attack. The short story on this is that any information received from a client has to be suspect. You cannot be guaranteed, there is no way to guarantee that information is any good. So, did you jump one? All right, let's see. All right, so let's talk about something with a little more security for a little bit here. The MMORPG space has been dealing with this problem for a long time. It's significantly older, significantly more involved than the casual game space. And the short solution is they don't trust the client. The client is considered a smart I/O device. It shows the player a picture of the world that is local and is a representation of the client's best guess as what the world is on the server, but the world is really kept on the server, and all the game state is kept on the server. Input may be modeled locally so you don't see any obvious lag. So when you move, it moves you right away on the screen, but it's also communicating that back to the server, and the server is doing its own checks to make sure you're not telling me I'm moving through a wall, for instance, or not. I say on the client, I attack, and you may see attack and attack swing, but actually the resolution of that attack, whether it hits, how much damage it does, etc., is all done on the server. At the server, I should mention, servers are only as secure as your data center. If you could have a perfect server-based game, and if that server is sitting out on the internet with wide open ports for anybody to mess with, it's no more secure from hackers than anything else. The enterprise solution for a long time for this has been you hire what's called a white hat. And this is somebody who is very, very, very good at breaking and cracking servers, but rather than breaking and cracking servers maliciously, he's in the business of cracking into your server and telling you how to prevent other people from doing it. One of the great white hats I don't know if he's consulting anymore, I know he's around more, but back in 10, we hired a guy named Dan Farmer, who wrote a program that you may have heard in history called Satan, which was one of the first security checking programs for internet servers. And Dan did we did the best we could to lock it down, then Dan basically spent about a week attacking it and gave us a list of things we had to do, ports we had missed, things we had running on our servers we didn't want to expose to the public or we wanted to turn off, that sort of thing. So, all the security comes at a cost, unfortunately. Gameplay execution is expensive. Now, when we talked about the first couple models, all the actual gameplay execution, all the logic is on the client. That's great because it scales automatically. As more clients show up, they bring their own supercomputers with them, and I get more computer power to run more people. It's not true when we have execution on the server. All of this MMO execution has a cost. In general, you can get about 1/10 the number of peak concurrent users on an MMORPG server than you can or need to on a casual game server. We're talking numbers in the thousands rather than 10,000s. And that's a good server, it has thousands, maybe as small as 500 depending on what you're doing and how you coded it. This is a premium service for premium users. This is short, and that's the reason for that picture there. It costs more per user to operate. That's just the flat out. It costs many more servers to run it. Those servers cost money, whether you're getting them with Amazon or building or putting them in yourself. Luckily, the revenue per concurrent user is much higher in these games. The revenue is, rather than being 10 cents, $10 a month, is more like $50, $150 a month. So we're talking 5 to 15 times the revenue, so the revenue return, which means that the economics work for this kind of game. I should also mention that you don't have, one reason why the revenue return is so high is because everybody who's there is paying you. You might have, some games might have like first 3 levels free as or so much to play for free, or first 2 weeks free as a way to get people in. That's what we call marketing costs. You're paying that. That's part of your marketing budget. The actual cost per user is fixed. Everybody's paying it, as opposed to free-to-play games where people come, then you have to entice them to pay. And in general, if you get 2% of your market paying, that's pretty good in a free-to-play game. So, well, all that precursor explaining why we did what we did with Zoo Kingdom. We wanted to try to get both of these qualities. We wanted to get the scalability, the low cost per user, but we also really wanted it to be secure. I should mention, I mentioned the direct monetary costs of security in terms of cheating. There are also indirect costs that cheaters tend to discourage other people from playing your games. It tends to be less of an effect in a single-player game because there's less interaction between them and there's less worrying about a comparison with what somebody else is doing. But in a multiplayer game, if I know somebody else can get ahead faster than I can because he's cheating, that's very discouraging. That drives people away from the game. It frustrates them. So what's our solution? Basically, we said, all right, we have to put the game state in the server. There's no good way around that. And we've talked about this in question and answer. Yes, there are technologies that try to make hacking the client harder, but that's an arms race, and those arms races honestly can't win. For every program out there like Punkbusters that tries to make it harder, there are hackers writing new hacks and new scripts to get around it. And Punkbusters costs you and costs them to develop, whereas the hackers are free. So it's really a losing battle. So we had to be the server, but we wanted to minimize our costs, and we did that in a number of ways. First of all, we focused very heavily on event-driven logic. I'll talk a lot more about that, why it's important for the server. So I'll reach these points actually. We went for an efficient communication scheme. We purposely designed the game to be low load in its design. And we made full use of multiple floors, because multiple floors are cheap. And the better you can scale out these days across multiple floors, the more efficient you are doing that, and more multi-threaded, multitasking can be, the cheaper your operation is. Did I miss the slide again? Did you jump on me? All right. Is that the right one? Yeah, okay. There we go. Next slide. All right. An observation we had looking at the space. Most of the time, Facebook games are doing absolutely nothing. That's the fact of the matter. If you look at these games, the classic game everybody emulates models is Farmville. Farmville is a game where almost literally the point of the game is to watch grass grow. You plant your crops, and then you sit and you wait for them to grow up. And once they're grown up, you harvest them, do a little work, you plant more crops, and you sit and you wait again. Particularly in Zoo Kingdom, we were very early on, we saw that our gameplay was going to be bursty, as we call it. What does this mean? This means that there will be small periods of intense activity. In Zoo Kingdom is a sort of a Facebook equivalent of the Zoo Tycoon series. You're laying out a zoo and you're caring for the animals in the zoo. So when you generally first log on to the game per day, there's a burst. They may do some moving things around. They will do all the care for their animals. But then there's a big waiting time. Care cycles, we measure everything in Zoo Kingdom, both buildings and animals and care cycles. And basically the game is you lay out your zoo and you watch these things, and sometime between hours and days, the monkeys decide they're hungry, the building decides it's dirty, you click on it to clean it, or you click on it to feed the monkey, and then it starts again. Yeah, I don't know why people play these either, but trust me, they're very popular. Interestingly enough, this is ideal for event-driven architecture. So let's talk about what event-driven architecture is and why it's important. The most important thing about event-driven architecture is it doesn't poll. And polling is basically the computer going, are we there yet? Are we there yet? Are we there yet? Asking if there's something to do, checking the state. Interestingly enough, this is directly the opposite of most classic game development. Most classic game development, as most of you probably know, you sit in the game loop. And in fact, that's what you're doing. You're asking, is there something new? Render it. Is there something new? Render it. Going around in circles. You can do that on a single-player game, because, or on a game where the player owns the machine, because the player owns the whole machine. You're not doing anything else with it. So you can afford to sit there and spin, basically, and waste time. But a non-polling architecture basically says if it doesn't itch, don't scratch it. Okay? If there's nothing to do, then try to do nothing. In this case, all game logic is occurring as a result of a packet arrival at the server. When there are no packets, the server sleeps. When there are no packets from you, but there are packets from other people, well, it could be handling other people's packets, not worrying about you. An event is a common term used as an event-driven architecture. In this case, in the server, the event that we respond to, in almost all cases, is packet arrival. A piece of data is arrived, what do we do with it? So as I said, ticking happens a lot. People hit the space again because they're thinking in terms of how they've written single-player or end-user client games. They go, okay, I have a monster. Right? The monster has to wake up every 1 second and check to see if anybody's around to attack. That's a tick. Ticks waste processor for just the reason we're talking about. It's making the server do work just to see if there's work to do. What we did in Zoom Kingdom, wherever possible, is we inverted the control, which is to say we had the client do the asking things like, is this monkey hungry yet? The client can sit there and spin, that's okay. When the client thinks the monkey is hungry, we'll talk about this more, it actually sends a packet to the server saying, hey, I think the monkey is hungry. And then the server can wake up and respond to it and check. So this is a little more detail on that. So taking a look at that care cycle, there's basically 3 ways you can approach it. The typical way it's done in most games, these giant client sitting there in a loop, or has a timer, which is about the same thing. It goes, okay, it's ready, monkey is hungry, show the monkey is hungry, deal with it, and then tell the server the result. Well, that, of course, is you can cheat it. Cheat engine allows you to do things like just change your clock rate, speed it up, change the... cheat engine, by the way, is a cheating VM. It's a virtual machine that is designed specifically to cheat with, that you run your game client under. Anybody haven't seen it. Very clever, actually. But one thing you can do is you can just say, oh, okay, let's run our virtual CPU speed at 10 times the rate for a while. Costly approach is just to take on the server. And that's costly because it's not so bad when I have 1 monkey, but think about now I have maybe 50 monkeys and other animals per zoo, and I have 10,000 people connected with their zoos. This becomes a lot of monkeys. So as I mentioned, what we did was we inverted control. We said, okay, the client can time it, but the client is not the final arbiter. When the client thinks the monkey is ready, it sends a packet to the server and says, I think this monkey is hungry. The server then responds with a packet saying, yes, I agree, it's been that much time, or no, I don't agree. And even if they hack their client so they ignore the don't agree, it doesn't matter because the state's on the server. And when they send a packet saying, I fed the monkey, the server's just going to go, you can't feed the monkey, it's not time yet.
Question.
Yeah.
So if you have something moving around, it's an AI moving around, it generates events.
We'll get there. The short answer is, I have a slide, anything we couldn't reverse control on or otherwise make event-driven, we eliminated from our design. Yeah.
So it seems that feeding animals is something that you wouldn't want happening. What if the client blocks the packet that's going to tell you that the animal is hungry, so that you never get the message that the animal is hungry? Would that be?
Well, the answer is they've cheated themselves in the negative.
Oh, really?
The way Zoom Kingdom rules are set up, most of these games are, you actually want the animal, the monkey to be hungry because you get points, you get money when you feed it. So that's the short answer. Yes, if we actually had a negative quantity, we would have to be trickier about it. And some of the games we're working on now, we do. But what we do then is when the player tries to do anything else, we check those stats and ask how much time has passed and adjust them. Partial answer to your question, I say we avoided things that we couldn't reverse, but for instance, we did have originally designed, we took it out because it confused the players, it was actually too much fun. We have guests that wander around the zoo, and when they arrived at buildings, they would basically give you some points for looking at that exhibit. What we did there was we basically let the client say, the motion is starting, this is where I'm going, this is my path. And at the end it said, I'm here. And then we just did a static check saying, okay, could we get from here to here in this amount of time? Is it reasonable? As long as it's reasonable, we let it through. There's really two approaches to doing servers like this. The first approach that was used in a lot of games is just literally to model the entire game on the server. A little more sophisticated approach has to do with actually validation checks rather than literal modeling of the game state. So what you're doing is not so much saying, okay, now I can move this piece over here on the game board, but is it reasonable this piece just moved over here on the game board? Does it violate any rules? So I mentioned I talked about this. Oh, we lost my animation. I'm so transferring it from PowerPoint. I'm bummed. The animation you can't see is the phone rings, guy picks up the phone, lines come out, puts the phone back down. Phone rings, picks it up, lines come out, puts the phone back down. That's HTTP, okay? Using HTTP for a packet stream is like hanging up and down on your phone for every sentence of a conversation. And the reason is this. As I mentioned before, every HTTP request makes a TCP/IP connection, which is a way to connect your two endpoints, sends some data, gets some data, disconnects. Termination. That's what costs the most in terms of chatter back and forth. As it's being negotiated, that's what costs the most in terms of actual processor time. The other part of TCP/IP that makes this expensive is because of the congestion control mechanisms in TCP/IP. Although you have a theoretical bandwidth you can send on your wire, how much data you can send per second, the TCP/IP connection doesn't immediately fill that bandwidth. It actually ramps up how much it's using. And this is part of a much more complex thing. You can probably have a whole 50-minute talk on. That's how TCP/IP tries to prevent anybody from flooding the internet. But the end result is that you're using the worst period of the TCP/IP connection for transferring data, which is that beginning part, over and over and over again. Our solution was to say, screw that. Make a TCP/IP connection for the game. As long as you're playing the game, it's connected, and just trade packets when needed.
So comment? So
Yeah.
the newest version of HTTP, though, does persistent connections, right?
So WebSockets. Yes, WebSockets is a hack on top of HTTP. So before WebSockets, the way you got what looked like a persistent connection was something actually the term really means more, but it's usually just referred to as AJAX. And you can also think of this as long. One of the techniques most common is a technique called long polling, where basically the way it would work is that the client, I mentioned that the protocol is I connect, I send a request, I get something back. The way long polling works is that I connect, I get something back, I immediately reconnect. And I just wait for the server to have something sent back to me. Now there's a timeout that you can't avoid in HTTP, so it's possible that will time out before you get the packet back. In the long polling scheme, you say, okay, timed out, do it again. Reconnect. So you kind of span the server with connections. A slightly better version of this, if you're willing to use lag, is to have a periodic poll. Where you periodically go to the server and say, what stacked up for me while I was waiting? Again, all these still do multiple connections. Now, WebSockets is an attempt to fix that. What WebSockets in HTTP 5 does is it allows you to actually make a connection, TCP/IP connection once, and trade multiple packets. What they've basically done is take what TCP/IP does normally, put a thing on top of it that doesn't do that, and then put another thing on top of it that does that again. There are other inefficiencies just involved in building up that stack. But yes, the other thing about WebSockets is it's all still HTTP text communication. That's the next one using TCP/IP. We just push bits back and forth, which is a lot smaller for the same amount of information and a lot less work, ultimately, to process. All right, so I mentioned, say before, if it was computationally expensive, we couldn't figure out a way to reverse the logic, we just didn't do it. Now in practice, we ran into this almost never, but there were a couple of times when we were close to give a clever solution, and there may be one or two features where we just said, no, we can't do it that way. That's going to be too much of the cost on the server, so we'll just come up with something else that accomplishes the same game design solution. And this is very common in game design. I assume you guys have run it, and some class have talked about this. But game design, in the end, is all about your intent in terms of the player experience and the player's reaction to it. How that's done is just a detail in getting to the player, and almost all game design, you end up taking what you want to do, saying, how does the system we're working with function? And then saying, well, how do we get from here to there? I like to say game design is, in some ways, is a lot like magic. There's a lot of smoke and mirrors. Interestingly enough, this is becoming a little less true in the very recent history, just because your machines on your desk have become so incredibly powerful, you can actually afford to waste some processor in game design. If you look at older games, you'll see that, for instance, there's no such thing as physics. There's things that may look like physics, but anything other than a very simple, like Newtonian line, is cheated. And this is because, as a game player, I don't care that the real world is properly simulated. Now, the military cares to some degree, and scientists really care. But game development is not about simulation, it's about experience. The same way movies are not about creating the real world, but creating an experience that feels real. All right, another big thing we did was we took advantage of the slow pace. Anything that happens on the client was effectively free to us, and what was actually the actual evolution of the state of the game is very, very slow. Which means most of the time, just like you're doing nothing, the server's doing nothing. Now, we do things to keep it visually interesting, so we do still have the guests, even though they actually no longer do anything game-wise. But they wander around the zoo, and there's little animations. That's all being done by the Flash engine on the game client, and we don't care. Another thing we looked at, caching. Use caching on a couple of levels. The first one, this is one nice thing. This is one of the things that HTTP does for you that's actually kind of nice when you use it for things it's designed for. Most browsers have pretty nice caching built in. So all of our static data, descriptions of how the animals look, how they animate, the values that you see in the store. Now, we also have those values on the server to double check that when you buy something, you're really paying the right amount. But for display purposes, we have it on the client as well. All that data we actually have in a set of XML files. HTTP is great at this is exactly what it's designed for. It's getting a big hunk of data, particularly text data like XML, and downloading it for you so you can look at it. So we have the browser go get that stuff for us. And the browser cache actually holds it for us. We then cache some of that. We read that, which does cost something, and some of that data we read, we actually cache secondarily in memory. So for instance, we don't go and reread the costs for animals every time you open the store, because that would put a lag in the store. So we just cache that stuff. Some of the stuff we cache you might be surprised about. So for instance, one of the things Zoo Kingdom does is it shows your other people you're playing with, your friends, who are also playing the game, and their level. If you click on them, this is one of our few pseudo multiplayer things. You actually get to see what their zoo looks like currently. I'll put currently in quotes, because that operation, when I get into the architecture, I'll show you how we sharded it out. I'm actually kind of, I very want my time. But that operation potentially actually involves contacting other game servers. And we didn't want to get in a situation where that kind of communication was happening all the time, where we could get back into sort of an n-square world. So what we do actually is we cache that. So and we know if you last looked at, if I last got your friend's level less than like an hour ago, or you looked at his zoo less than an hour ago, if you go back, you're going to see the same thing, even if you level, even if you change the zoo. And that's just a way we can reduce the amount of traffic on our back end that we have to deal with. But again, to the player, it's not that important. That's sort of the big takeaway that bothers us. If it's not a security or gameplay affecting issue, then we try to push it to the client. So let's talk about architecture. We talked about the design sort of goals and approach. This is what our system looks like in a networking diagram, in a systems diagram. Our client is Flash-based, so it's running inside of a web browser. And there are a number of things that happen I'll talk about here. That's the big picture of the system. I'm going to talk about each piece separately. Just dive down a bit. So this is the easiest part so far. I mentioned that our XML, we have the data in XML files. We also have all our static content. So our Flash game Swift code, our Swifts that hold args, etc. All of this stuff is deployed out on what's called a content delivery network. We use AS3 CloudFront, another content delivery network you may have heard of is Akamai. And what a content delivery network is this is basically a set of server rooms. The person who runs the content delivery network is set up around the globe, if it's a global network, such as these are. And they're placed in places where they will have reasonably fast connectivity to a group of users. So I think there's an east and west for Amazon. And that has to do with the fact that there's some congestion going across East Coast to West Coast in the middle, in the design, the way the network is laid out, network topology today in the US. They have a machine room in Singapore that serves pieces of Asia. I think they have one in Europe somewhere. What we do is we push our data out to that. We give it to Amazon, and Amazon pushes out to those servers. And that gives us two things. First of all, it gives us good response time downloading that stuff. Secondarily, it's actually a pretty inexpensive way to push data out. This is a system that's just been optimized for getting data to clients. So what they charge us is the same cost per byte going out or coming in as they would charge us for running an Apache server in like EC2 in the virtual cloud. We don't have to pay for that Apache server. They're paying for all the servers. It also scales by itself. Don't worry about it. It's magic. They built a scalable system. It scales out and handles the load. Starting in some more interesting parts of the system here. We do have a small cluster of Apache servers. Well, we're actually running two. The reason for that is the content delivery system is great for what called static content. Things are just blocks of data coming down. But it's not programmable. You can't run servlets or PHP or Perl or anything like that on that. We have some need for some PHP servers. And so for that, we run our own little Apache cluster. And there's really 3 times those Apache clusters used. One really isn't shown there. But one is when we're connecting to Facebook, the initial login sequence. Now, I'll talk about that a little more. That's to do with the fact, again, that's to do with the fact that Facebook, although there's a number of ways to connect to it, really likes PHP the best. It's also used when we have web service calls that refer to a particular user. So for instance, when you buy what we call blue certs, our currency at OfferPal. OfferPal makes a web service call to us saying how much was bought. However, as I mentioned before, and I'll show you in a minute, we're actually sharded out invisibly in multiple servers handling the users. That has to get routed and directed to the right server for that user. And our PHP layer also does that. Third thing it does, that's basically what it does. This subset is it actually handles compliant. The client occasionally has stuff it wants to do. It talks to either Facebook or to our statistics tracking layer. We also use it to proxy for that. Did I miss a page, or did I just? Let's see. Or is it just 23, 22? No, okay. So this is jumping a little bit. I'm sorry, we'll get into that. I mentioned that redirect. So let's talk about redirect a bit. The way that redirect works is that we have actually now I got went too far. Thank you. On 23.
Hey, wait again.
Come on. 25, 24. There. Back. Up. Too far. All right. So 2, 3. Okay. A little bit of lag. Network. Web cluster. All right. As I said, this is my driver of the thought. I've already organized a couple slides. The way that proxying works, the way that routing works, we have an issue that we figure we can get up to about somewhere with our game, we tested between 5,000 and 10,000 currently connected users on a server, which is a lot better than you get an MMORPG server, but it's still not enough to handle the kind of load you're looking at in the Facebook game. I mean, Facebook games potentially, as I say, could be many tens of thousands of users connected. In practice, we want to handle loads up to about 30,000 users. In terms of, and then we want to go scale up further. We want to be able to do that without any further scaling. So the solution in the MMO industry has been, well, there's two levels. First of all, they break the world into what we call zones, which are basically play areas. And then, since even that doesn't get them to the level they need to, they then take those worlds, they replicate them. And when you log on to, again, a game like EverQuest or WoW or whatever, you're typically told to pick a server and play on. The reason it's called a server is historical, and I can hold a separate talk about why that is, talk about the question and answer. But that server is really a name for what in the industry is called a shard, which is a set of servers. It's an entire replicated game backend. So it's all the different zone servers and the supporting servers for one instance of that game. That's why you can't play with somebody who's on another server unless they move data around or do other things for you. We wanted to do that, but we didn't want to expose that to the Facebook players, because our Facebook players are your grandparents, parents, okay? They're not going to understand that stuff. So what we did instead, we said, okay, we're going to separate them out into groups. But the way we do that is we do it by Facebook ID. And what we do is we take the Facebook ID, which is a string, and we put it through a second redundancy check calculation, which basically just gives us a well-distributed number, the number of well-distributed bits, which is to say that given the population of users, we're going to get, somewhere in that population, we're going to get a fairly even distribution of people who have a 1 or a 0 in this particular place. What we then do is we then use that as a key to a tree that's a map. Starting with the least significant bit, we say, okay, is that bottom bit in binary, is that a 0 or a 1? Well, if it's a 0, we're going to go to that side of the tree, and if it's a 1, we're going to go to that side of the tree. This is what's called an extensible hash. The reason it's extensible is because we can start with that and just have two servers, 0, 1. However, let's say one server fills up. Well, what we can do is we can take the server that in this case was on the one side and split that and say, okay, now we're going to take half the users, put them on one server, take half the users, put them on another server, and we'll determine which one by the next bit. And so what you end up is with a tree, you can keep on extending. Now, this diagram is a little bit, it's there for illustrative purposes. It's not quite the way things work out in the real world. The reason I say this is because we get such a good even distribution, in fact, our servers tend to fill up at an even rate, which means that in reality, we tend to go down the entire level of the tree each time, which makes scaling a little expensive. Each time it doubles our number of machines, but each time we get double capacity. And so what this allows us to do is to start with a single machine, then go to 2, we're up to 4 at the moment, and we could go to 8 or 16 if we needed to. As you mentioned, it says copy EV to leaves. This has to do with the Red Dwarf server I'll talk about, but basically it's a local database for information on each user that's actually playing on that server. So that's the server cluster I mentioned. PDS, we refer to it as the PDS cluster or the Darkstar cluster. PDS is Project Darkstar Server. Again, for historical reasons, the changeover to the name Red Dwarf happened after we started this project. So you'll kind of see me use those two terms interchangeably to some degree. What does it do? Well, first of all, it handles our game logic and maintains our game state. So it also has database involved. It also handles, all those packets coming in saying, it's time to feed my monkey, I'm feeding my monkey, I'm putting this building here, etc. It also handles the credits from OfferPal. And the way this actually works is that the Red Dwarf or Darkstar servers are extensible, and you can actually plug in, it's almost like on a driver level, new components, they're called services. And in this case, we wrote a service that uses a little mini web server called Jetty that faces out to the web and allows web connections to come in. And then those get translated to events so that it can bubble up to the system. It's purely event-driven, and the Darkstar servers help us with this because it's actually, although there is a way to tick, it's not recommended, it is built as an event-driven system. That's its architecture. Darkstar, if any of you are familiar with Java 2 Enterprise Edition or servlets, servlets are a web content container, or this web, sorry, Tomcat or Glassfish, a servlet container, is a web service container, which is to say that it handles all the details of connection, communication, etc. You just write the logic, which is the servlet that goes into the container. Darkstar is an event-driven game logic container. Does the same thing. So it handles all the connection for us. It translates packets coming into events. It actually does some other things, like it's not only event-driven, it's transactional, which is part of how it handles scaling, which I can dive into later in questions. I'm running a little late, sorry. I'll go too deep into that. But it actually protects us against things like the server going down when an operation is half completed, either the operation is fully completed or it's not at all. It also actually self-multi-threads. As long as you follow its rules about how you write event-driven code, you don't have to think about multi-threading. Those of you who've done Java may be familiar with the synchronized keyword. If you ever see the synchronized keyword in regular app code, it's wrong. And actually, it's harmful. It handles the multi-threading. It scales out very nicely across the number of processors you have. And in question and answer, I can talk about how that works. If anybody hasn't heard of my other talks about that and is curious. The end result of this is, on an estimate, we think we can get good gameplay with somewhere over 10,000 players today on one of our servers. We've tested to 100,000 simulated, and there's important differences between simulated and real. I can get this into that are also separate. I don't think we can actually reach 100,000 players real, because that simulated 100,000 players actually was not 100,000 connections, and there are costs in the operating system for connections we can get into. But as load, we put the load on the 100,000 players would, and although it got laggy, it kept working. That's the Red Dwarf website, by the way, if you're curious about technology. So, as we mentioned, we do visible sharding based on the Facebook ID. We have a back channel. So in general, what you do in your game state exists on your server only. For that information I mentioned before, what your friend Zoo looks like, what his level is, that sort of that information. Again, he may not be on your server, because he may have a 1 where you have a 0. So what we have there is we actually, the Darkstar servers use the same map, and they go out and call out to the server room when they need information and say, what's this guy's level? What's his zoo? Now we don't want, that could become a nightmare, because potentially all your friends could be on different servers, and if you're hitting them, now that becomes the 1 n squared problem, where every server is trying to talk to every other server at once. So this is why we cache these things and limit how often they can happen. Just wait a minute, we will need to help. I'll pick up again in the next one. All right. The next part of the system, which is not actually something that all game builders think about, but turns out to actually be a reasonably hard problem, is statistics tracking. What you need to understand, as I mentioned before, these games are driven by, the money is driven by object sales and sales to be able to do special things in the game, like there's a button you can press, and for 1 blue cert, it will feed your entire zoo at once for you. Things like this. The way you make this effective is that you need to have marketing information. You need to understand how people are playing your game and what they do or don't spend money on. Little dark secret of Zynga, okay? Many people don't realize this. In many ways, Zynga, who was the most successful in the space, is not a game company. I knew a guy who ran a marketing group who sold panelized house systems. I won't get into what that is. The important thing is, he told me one day, he said, Jeff, we're not a panelized house company. We're a sales and marketing company. Panelized houses are just our widgets. The point being, you could be selling anything, same techniques. Well, Zynga is a sales and marketing company. Gameplay and virtual items are their widgets. Most of Zynga's effort goes into this, goes into statistics tracking, and they are the best in the business at this. They don't apply this to bug fixing. They push things out, they know they're buggy, but they use data coming back, what people are and aren't doing, to decide whether a bug is worth fixing or not. If a bug is not driving people if a bug is not getting in the way of people spending money, if a bug is not driving people away from where they want them to go, it's not worth fixing. We'll see if this is long-term sustainable, but it's been very successful so far. Zynga is really, they are brilliant at this, which is using statistical analysis to move masses of people where they want to move from. I like to think we're not quite that evil, but we do still need to do this to drive our development, know what's worth putting money into and what's not. So we use statistic tracking for that, to know, for instance, what's selling. Like we put out this very expensive dragon recently. It's a limited item creature. Sold fantastic. We need to know that. We need to know that our customers will spend 10 times what they spent on some of the other animals if it's cool and limited. The other thing we actually do with this, which I think is actually kind of nice, is we do so much tracking of what people are doing. It actually makes it pretty easy for us to find bugs. Like in the early days, we tracked every step in the startup process. And we put a packet back to our server. And we could draw a chart and say, oh, you know what? 20% of our players are not getting past the connect 50% of the time. That's a problem. Why is that happening? We go and find it, we fix it. So statistics tracking, it turns out, in these mass markets, that's the way you understand your market. It's absolutely critical. So our statistics backend, and I showed you from the PDS cluster, most of our data comes from the game servers. However, I mentioned, for instance, that logon sequence, that actually comes from the client. The client makes a web call to our PHP server and then does the same thing the PDS server cluster does, which is it sticks a message in a message queue. Now, a message queue is something the enterprise developers came up with. It's a very nice and handy thing, this sort of thing. Message queue is just basically a server that keeps a big queue of messages waiting to be read. However, these servers are designed to be fault tolerant. So for instance, if a server dies, you don't necessarily lose everything that's in the queue. It's replicated other places. It's also designed to scale out for you again. We use Amazon's SQS, Simple Queue Service, which is a web service-based message queue. And again, the nice thing about that is we didn't have to worry about building out a message queue. They built it. To us, it's a black box. It scales. It works. It's never lost a piece of data for us. Now, one of the advantages of that, first of all, is if our servers go down, our web servers go down, we don't lose data because the data backs up in the queue. When it comes back up, we read it back in. I also mentioned that gameplay is bursty in the beginning. Because of that, our data is bursty. So sometimes we'll get data rates that are too fast for our MySQL processors to handle them. But the overall average throughput is fine for them. What that means in practice is that it backs up in the queue when it's coming in fast and furious, and then when we're in those low periods, the MySQL server just walks along reading that queue and putting it in our database for us. I should mention that we have a couple other web servers that just go to that web server, that database every so often, do SQL queries on it, and plot nice charts. So our business intelligence people can look at the charts and see what's going on. All right, really briefly, the most complex part of this whole thing, making it work, I wanted to take a little time to talk about. And that is the handshake with Facebook. It took us some time to get right. I thought it was worth digging into here. So I'm not sure which, that's a sequence diagram. It might be easiest to look at both of these. That's the wrong way. On the large, what happens is the client browser says to Facebook, I want to go to this app. It does that by sending a URL, a get. It says, get me apps.facebook.com/ZooKingdom. What Facebook does is that Facebook has registered with us a URL on our PHP servers. And it in turn makes a web address to us for the contents of what is going to be an iframe on that page, which is basically a web page that's embedded into your web page. That request comes with a bunch of information. It comes with the Facebook user ID. It comes with authentication information, so we know it's really Facebook talking to us. There's a secret key that they've given us that only we know, that they know. There's also a reverse key they've given us. We used to talk to them, so they know we're talking to them. That's other security. There's actually an Apache call we make. We get that stuff, it validates it all, a PHP call. And then what we do is we actually cook a web page we send back. And that web page, most of it contains is a Flash programming location. However, in there is something called flash bars. The flash bars are, and this is actually the sequence diagram is what I use here. Flash bars are how you get data into Flash. They're basically like parameters on a command line. And so what that passes us in is a number of things. First of all, PHP looks up what node we want to be on, the Darkstar node, the Dwarf node, based on that table we just talked about. Second of all, it returns the user ID, the Facebook user ID, which we use to log into that system. Then the third thing we do is we actually take that user ID and we do a hash for the key only we know. What that produces is something that we call a password. It looks like a password, it's used like a password, but it's going to be created with somebody who knows that hash key. The Flash program that starts up, it uses that information to connect to the Darkstar node and start the game. The first thing the Darkstar node asks for is name and password. It passes in the Facebook ID along with that hash. And what the Darkstar server does is it has the same key. And so it hashes the user ID as well and checks the passwords against each other. And if it gets the same result, it knows that whoever's talking to it at least knew the secret key. As long as that hasn't leaked out, we know we've got a secure connection. Now, this is not totally secure because this has the same problem that open text passwords do. That we're passing this thing around, it's effectively a password in a packet that if somebody can intercept it, they can actually read and get that password. However, it's good enough for our audience, is basically our reaction here. I mean, if you look at almost every MMORPG, they do exactly the same thing. They send you password in open text, so clear text. It takes a pretty sophisticated attack to get that. To get that, you either have to have, it's a man-in-the-middle attack. Either you have to get like a virus or a piece of software on the guy's system that worms into his communication stack to read that, or they have to actually be able to get in at one of the routers that's passing the data along in order to see it. This sort of gets into you guys know the story about the two guys camping and they hear a lion in the middle of the night? It's a very old security story. Well, one guy, they're African, and they hear a lion roar, and one guy gets up, puts his sneakers on, goes back, calls back his sleeping bag. And the other guy says, what are you doing? If that lion attacks, sneakers aren't going to help you. You can't outrun the lion. He says, I don't have to outrun the lion, I just have to outrun you. There is a certain level of security where you make it hard enough that you're not a good enough target and people go elsewhere. That's basically the login sequence as it happens. I should mention that we originally tried to do this another way. Originally tried to do this just like that's in the Facebook ID and using Facebook's Java API, because the Darkstar service program in Java, to authenticate that directly with Facebook, using their keys. There's a lot of problems with Facebook. If you do Facebook programming, be aware, Facebook is inherently an unreliable service. We were getting about 20% failure doing that. So we tried the PHP, which by the way is what Facebook programs in. It's PHP. That worked much better. So out of curiosity, we actually got a whole sources available, dug in a source of both and saw why. And the Java API just calls your web service and tries to do it, and it doesn't get it back in time, it fails. The PHP code has about 4 layers of fallback for things that don't work. Because a lot of the time, a lot of Facebook doesn't work. This is a general rule you should also be aware of. We do things throughout. We had to learn this the hard way. We now know it as part of our development pattern. We have fallbacks in the game for if we don't get the level from Facebook that we're asking for, if we don't get pictures, because basically you send a request to Facebook and it's a request. And if Facebook is feeling nice, it will answer. Not entirely their fault. I mean, to some degree it is, but really what it comes down to is their primary concern is serving their own pages and serving their own primary functionality. And if they're at all overloaded, they will basically throw you away and deal with their own shit instead. Pardon my French. So, this is sort of a summary. Where we got on this. We got to a reasonably secure server. It has some advantages over the traditional approaches. One is that, because we have that connection, it's always connected actually, we can do things that are synchronous. For instance, when you buy currency, at OfferPal. As soon as OfferPal is done processing that, it gives us a call, it shows up on your client. Gifts. You send them to, I'm sitting next to you and I send a gift to you, game to game. I send you a Tiger Cup. It shows up pretty much immediately, and a box comes up. I say pretty much because depending on load and such, it might take a minute. It's also multiplayer play ready because of this. One of the things we have discussed is the idea of doing instant auctions.